Yep, then I can tell it's recording now. So, welcome everyone. I see a few more trickling in as it gets to be 6:30. So what I thought I would do is go over the old exam that I posted from 2020 when everything was all messed up. All our exams were online and so forth. So, the first part of this exam was from chapter 27, and you are likely to get questions something like this as well. It's basically matching. Before I do that, I want to take care of something else in ChemDraw. I did this in my Tuesday, Thursday classes. I didn't have a chance to do it today in my Monday, Wednesday, Friday class. There's some abbreviations that I think are worth knowing. First of all, if you see CO2H, that means C double bond O, OH. In recent years, I've taken to not using these abbreviations, but I see they're used on the practice exam. And so I want to make sure that everyone understands. So CO2H means C double bond O, OH. It means a carboxylic acid group. CO2 minus, as you might therefore guess, means C double bond O, O minus. CO2 ethyl. Means C double bond O, O ethyl. I don't know why it did that. And last but not least, another abbreviation you might run into is CHO. Now, as I said, I'm trying to avoid using these nowadays, both in class and on my exams, but I see they're used on the practice exam and are in the answer key as well. So I just want to make sure that everyone understands. And CHO means C double bond O, H. In other words, over here we have a carboxylate ion. Over here we have an ethyl ester. And sure, you can also write CO2CH3 for C double bond O, OCH3. That works also. And finally, CHO is short for an aldehyde group. I just wanted to make sure everyone knew what those abbreviations were. You can use them if you like. My experience in recent years is that they are confusing for students. So I've avoided using them for that very reason. Okay, and my apologies to those of you who are in Tuesday, Thursday, and have been through all this already, but I didn't get a chance to say this in my Monday, Wednesday, Friday class today. So as long as you keep those things in mind, you'll be able to understand what's going on in both the exam and the answer key. So the first one, uh-oh. Yeah, some of my keys are sticking. I kind of sort of spilled coffee on my keyboard the other day, so very human problem. So let's take a look at the oh, this is the answer key. I don't want the answer key. I want the regular exam, which has the structures. So the first question was for soap. And in class, we said that a soap is a sodium or potassium carboxylate of a long chain fatty acid. And there are a few structures here that look like fatty acids. This one does. This one flat out is a fatty acid. This one is a long chain ester of a long chain carboxylic acid. And then we have this one, which is the sodium salt of the carboxylate ion. Remember, CO2 minus is C double bond O, O minus. So that's the soap. The soap is C. B is a fatty acid. And G is closely related. G is a wax. A wax is a long chain ester of a fatty acid. And you see we have the residue of a long chain alcohol over here, having reacted with a 16 carbon fatty acid. Steroid hormone. Well, the only one that could be a steroid hormone here is A. We just have to be careful to see whether this is a bile salt or not. And in class, we said that a bile salt has the same 4-ring appearance as a steroid hormone, but in between the A and B rings, there's a cis ring fusion. In other words, the two groups, if there are two groups here between the A and B rings, that is the first and second ring on the left, if there are two groups here, they must be cis. Well, this is only one group. There's a double bond at the other carbon. So there is no cis or trans distinction. So this is not a bile salt. This is a steroid hormone. And the correct answer for steroid hormone is A. Prostaglandin. In class, we said that a prostaglandin kind of looks like a fatty acid, except there's a 5-membered ring fused in the middle of it. And so D is our prostaglandin. Water-soluble vitamin. This is what we assign it if we're looking at something that looks evidently not fat-soluble, but water-soluble, and doesn't fit into any of the other categories. So it's not a triglyceride, it's not a prostaglandin, it's not what's that word? It's what this thing is. Terpene. It's not a terpene. It's not a wax. It's not a soap. And the best answer for that one, I think, is F. F looks very water soluble. You've got two OH groups on the phosphate. which is water soluble. You've got an OH group here, which can undergo hydrogen bonding with water. You've got a pyridine nitrogen, which can undergo hydrogen bonding with water. The aldehyde group also can undergo hydrogen bonding. So I think the best answer there is F. So those are the answers for that. I think it might be good if I took this whole picture here and just said what all of them are. Yes, I'll explain the prostaglandin again. This is a steroid hormone, not a bile salt. This is the prostaglandin, and the way you know it's a prostaglandin is that it looks kind of like a fatty acid, except there's a 5-membered ring in the middle of it. All prostaglandins seem to have a 5-membered ring. I don't know why. But a prostaglandin is what looks like a fatty acid, but with a 5-membered ring in the middle. And so that's what makes it a prostaglandin. This is a water-soluble vitamin. Up here, you've just got a long-chain carboxylic acid, which is a fatty acid. Over here is a soap. This is a wax. H was not used on this exam. And over here, we have to count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I count 10 carbons coming from 2 5-carbon isoprene units. 2 times 5 makes 10 carbons. And so that makes this compound, again, I've forgotten the word and I just said it, terpene. So the way you know it's a terpene is by the number of carbons. If it doesn't fit into any other category, and it has 10 carbons, it's a terpene. If it is 15 carbons, it's a sesquiterpene. Sesqui meaning 1.5 times 10 is 15. And if it is 20 carbons, it's a diterpene. Now, your page may not look exactly like this. You may have a bile salt. Let me show you what a bile salt looks like. That's no good. A bile salt will have a cis ring fusion. This is now a bile salt or bile acid. So that's how you tell the difference. You look between the first 2 rings, and if it's cis, it's a bile salt. If it's not cis, it's not a bile salt. Probably a steroid hormone of some kind. Could be cholesterol, but steroid hormone will do. So that's how you tell the difference. So don't expect to be given the identical structures and ask the exact same questions. You may not be. You'll probably get questions like that, but don't expect it to be exactly the same. All right, any other questions about those? Next question says, draw triglyceride, and we went over that in class. U15 get a special gift for being here at the oh, I guess it isn't a special gift just for you. because people might watch the video. All right, I'll give the people who watch the video a gift too. Here, well, actually, it says you're expected to know this structure. It didn't matter because that year it was all open book anyway. So you do not have to memorize the structure of glycerol. That's the only time I'll say that. But these people didn't have to memorize it either because they could just look it up. And remember, CH3, CH216, remember CO2H is C double bond O, OH. It's a fatty acid. So glycerol is 1,2,3 propane triol. Whoops. Not that glycerol is particularly difficult to learn, and we'll run into it again in chapter 29. So this is glycerol. To make it a triglyceride, you make it a triester with 3 carboxylic acid molecules. And again, you may be given a question like this, but don't expect that it will be the exact same fatty acid in the exact same answer. Read the question. The question might be different from on the practice exam. Don't just memorize the answers from the practice exam. That might not end well. So we're going to make a triester. It's not liking my bond angles, I'm quite sure. Whoops. And then we put the rest of it, which is 16 CH2s, then CH3. I'm worried something horrible will happen if I double click. I guess it's not too bad. I think that's still legible enough. CH3, CH2, 16. So that's how you draw a triglyceride. You take glycerol and you make a triester. I expect at this point you know what an ester is. So you just make it a triester. And don't memorize this answer. If there's one in your exam, it might be a different fatty acid. Make sense? Questions on that one? Let's see. Unfortunately, the one thing I do not have on this computer is any kind of stylus. And my screen is not a touch screen anyway. So in this question here, we're given a carbonyl compound and we're asked for the enol form. So I expect you to know what an enol looks like. To make the enol, you change C double bond O to C single bond OH, and you change the carbon-carbon single bond next door to a double bond. Can't make it any plainer than that. That's how you turn the keto form into the enol form. Then you're asked for the enolate that's formed upon treating it with sodium hydride and THF. This was actually a very easy question, because there's only one possible enolate. So we just need to draw the resonance forms. We can make it from the enol. And one of the resonance forms has the minus charge in oxygen. The other resonance form has the minus charge in carbon. I don't know why the program objects when I put the minus in, and now you can't see it because of the red circle. But that carbon should have a lone pair and a minus charge. So those are the two resonance forms of the enolate. Then it says, of the two resonance forms you just drew, circle the one that is the major contributor to the overall structure. And the major contributor is the minus charge in oxygen, because oxygen is electronegative. So that one is the major contributor. Then we move on to chapter 26 stuff. We're given the side chains of two amino acids. And it says to draw both amino acid molecules at pH 1 and then again at pH 14. We're given them at pH 7. So in class, we went over the structures of amino acids. Oh, that's no good. At pH 1, the carboxylic acid will be protonated. It's below the pKa of about 2.5. The amino group is certainly protonated. And then recall when in this shape, the hydrogen is pointing out and the side chain pointing in. So the hydrogen's on the wedge bond and the side chain on the dotted bond. Let me see if I can do this. Text flush right. Yes. And then this amino group is also protonated at pH 1. So at pH 1, everything that can be protonated gets protonated. At pH 14, it's not so. The amino group is the free amine or the amine-free base. Same thing on the side chain. And the carboxylic acid is also deprotonated at pH 14. At pH 14, we're above the pKa of all of those groups. So they're all in their deprotonated state. Actually, I'm going to do this. And then tyrosine. And tyrosine is CH2. Then the benzene ring. And OH in the para position. And that should be that. That's it. Oh, wait, I'm sorry. I'm at pH 1. So that means I need to protonate my amino group. There we go. Now we're good for pH 1. And now at pH 14, our amino group is again the amine-free base. The carboxylic acid is the carboxylate ion. And also the phenolate gets deprotonated. The phenol was on that table I gave you in class. Doesn't matter which class you're in, we did it in all 3 sections of the most common groups that you would run into. And we said that phenols have a pKa around 10. And so at pH 14, we're above that pKa. So this group will be deprotonated. Now, this is only for phenols. This is not for aliphatic alcohols, regular alcohols, like CH2OH. So serine would not be deprotonated, or threonine would not be deprotonated at pH 14. That's very important because I don't remember. You might be given serine or threonine. So those would not be deprotonated at pH 14, and making them deprotonated would lose points. So that leaves the dipeptide. We're doing tyrosine, then lysine. So to make the dipeptide, we start with tyrosine at pH 7. I'm not going to need that many. We start by convention at the nitrogen terminal. H is on the wedge bond.
Oh.
There's our tyrosine. And then comes the nitrogen of the next one, which is lysine. And now we've turned the molecule over. So now the H is going to be back on the side chain on the wedge bond. And as I recall, it was 5 CH2s and H3 plus. And then we come to the carboxylate terminal. And the carboxylate will be deprotonated because we're at pH 7. pH 7 is above the pKa of the carboxylic acid. So the carboxylic acid is deprotonated and exists as the carboxylate ion. And there you are. There's our dipeptide. With complete full stereochemistry. Questions on this problem at all?
So for the stereochemistry just in the initial molecules, how do we memorize like whether the side chain is behind or forward? Is it always just going to be behind?
I was anticipating that question. That's why I put these arrows here. What you want to look at is the shape of the carbon that has the side chain on it. If that carbon is pointing down like it is over here, then the side chain is on a dotted bond. If that carbon is pointing up like it is over here, then the side chain is on a wedge bond because the whole molecule got turned over. So there is no always here. It depends on the direction that that carbon is pointing in. Do you see how the little V or the little wedge is pointing down over here and the little wedge is pointing up over here? That changes the direction of the side chain. I could try to do something freaky with my hand and my fingers.
Okay, I see it.
This is doomed to failure. Good. So what do we have on the next page? Next page is our mechanisms. It would take me forever to draw out the mechanisms from scratch. So now I'll switch to the answer key. Just making sure I had the same thing. Yep, I think I did. So the first one is halogenation at the alpha carbon in acidic solution. Which we covered this week in Monday, Wednesday, Friday. I think we might have gotten it to already last week on Tuesday, Thursday. So recall the first step is protonation of the carbonyl oxygen. We need to look and see what the acid is. And again, remember CO2H is C double bond O, OH. So CH3CO2H means this. It's acetic acid. So we use one of the lone pairs on oxygen to pull a proton off of acetic acid and give us the acetate ion. The acetate ion is not a strongly basic anion, so it's okay in acidic solution. So here we've protonated the carbonyl oxygen. Then we pull off the alpha proton, move the electrons in between the two carbons to make a carbon-carbon double bond, and break the carbon-oxygen pi bond to get rid of the plus charge on oxygen, and we get the enol. The enol is going to be the major reactive species in acid. The enolate is going to be the major reactive species in base. That's something brilliant that I should write down. I mean, I want people to have some benefit for at least watching the video, if at all possible. Anyway, since we're in acidic solution, the enol is the major reactive species. The enol reacts with the elemental halogen that we're given, which is iodine. The electron pair folds down from the oxygen to reform the carbon-oxygen double bond. We break the carbon-carbon pi bond, and that attacks I+ from the iodine molecule. In class, I think we had Br2, but it doesn't really matter. It's the same type of thing. Then we break the weak halogen-halogen bond, put the electrons onto iodine to make I-, and we get this intermediate. And then all we need to do is deprotonate this species. We'll use an acetate ion, which is going to be present in some quantity in acetic acid. Again, acetate ion is okay in acidic solution. It's not a strongly basic anion. Acetate is fine. CH3O- is not fine. ETO- is not fine. OH- is not fine. NH2- is not fine. Acetate ion is fine. So the acetate ion pulls the proton off this oxygen, getting rid of the plus charge, and you have your product. Oh, I even put it here. Carboxylate ions are not strongly basic anions. Questions on that mechanism?
What's the difference between an enol and an enolate?
I need another page.
Mm.
To tell the difference between an enol and an enolate, look at the oxygen. I believe this is in the class notes. If it's OH and the species I'll draw examples too. Is neutral, it's an enol. If it's O minus and the species, or I should say, if there's no hydrogen attached, and the species is an anion, it's an enolate. So for example, enol. You can have the other resonance form of the enol too. Minus charge on that carbon. Also an enol. There's an H on the oxygen. And the overall thing is neutral. There's a plus charge and a minus charge, which altogether make neutral. Enolate. And by the way, those are resonance contributors. The other resonance contributor of the enolate follows the same rule. Enolate. Other resonance form. There's no H on the oxygen and it's an anion. Make sense?
Yes.
So to tell if it's an enol or an enolate, look at the O, look at the oxygen. That will tell you. Window, other one. So where was I? Right, so that's an enol because it is an H on the oxygen and the overall species is neutral. In the next problem, we're in base, not in acid. And this over here is alkaline hydrolysis of an amide, which we did go over in class. Both of these mechanisms we've gone over in class, and I don't promise you'll have the same mechanisms. I think I can promise that there'll at least be mechanisms we did in class. Will we need to draw the lone pairs in the exams? I will say whenever it needs to be clarified. You can tell whether you need to show lone pairs by what I've shown on the answer key. All lone pairs shown need to be shown. All lone pairs not shown do not need to be shown. It's a matter of keeping things clear. I would say if you're in doubt, then show all lone pairs. If you're in doubt and you want to play it safe, shall show all lone pairs. It's never wrong to draw them. Okay, so since we're in basic solution, we do not protonate the carbonyl oxygen first. Instead, we start with nucleophilic addition to the carbonyl. And we're given OH minus in water. So the only rational nucleophilic species is OH minus. That will attack the carbonyl. We break the carbon-oxygen pi bond and put the electrons on oxygen to make a minus charge. And then we need to protonate the nitrogen because we cannot lose NH2 minus, even in alkaline solution. NH2 minus is too strongly basic. So the pKa of this ammonium salt is around 10. So it's okay to use it in alkaline solution at pH 14, which is what we're probably at. So I realize this is a little confusing having both a minus and a plus charge in the same intermediate, but this is the correct way to draw it, and this is how we present it in class. And it's because the species can exist at pH 14. Basically assume pH 14 for basic solution and pH 1 for acidic solution. So once we've protonated that nitrogen, using a water molecule, we get this intermediate. Let's not gloss over the fact that we used a water molecule. Look at what we're given, OH minus and H2O. We haven't added the H3O plus yet. We're still dealing in basic solution, alkaline solution. So we have to protonate the NH2 using a water molecule, since H2O is what we're given. That gives us this intermediate. And then we lose ammonia as a leaving group. The lone pair in oxygen helps out by folding in and making a double bond. And we have a carboxylic acid. Carboxylic acids are acidic species. This is yet another one of those cases where we have formed an acidic species in base. And so we have to show the base deprotonating the acidic species. We can't avoid having to show this step because we've generated the carboxylic acid in basic solution. So that gives us the carboxylate ion. And then that's when we add the H3O plus. The first thing the H3O plus does is neutralize the OH minus that's left over. And then it starts putting the protons onto the carboxylate ion. So we show H3O plus putting a proton onto the carboxylate ion, and that gives us the final product. You may have more or fewer mechanisms on your exam. You will have mechanisms on your exam. After about the third exam in Organic 1, there are mechanisms in all organic exams. Even maybe the second exam might have some mechanisms in it. First exam, not so much in Organic 1. Oh, also your class notes should be updated with lists of reactions to know with mechanism and without the mechanism. I fear I might have forgotten one or two reactions. I'm not confident that that's absolutely every last one. I did my very best. But I feel I might have missed one. That should certainly be the vast majority of the reactions. Vast, vast majority. All right, any questions on those two mechanisms? What have I done? Let me just change that to what you're used to seeing. Let me do likewise over here. Pardon my bond angles. That's what you're used to seeing. So the first reaction is DCC coupling. DCC will couple a carboxylic acid to an amine to make an amide. And so you put the nitrogen of the amide right on the carbonyl. And just attach whatever alkyl group. Looks like there's a butyl group attached. So that's the answer to the first one. DCC brings together a carboxylic acid and an amine to make an amide. So you need to know what an amide is in order to be able to get a question like that right. DCC is also used in peptide synthesis. The next one is lithium aluminum hydride reduction of an ester. And the product is a primary alcohol. CH2OH. And the next one is alkylation of an enolate. This question's a little bit dirty. The way we did it this year was like this. So the sodium methoxide first pulls off a proton from in between those two carbonyl carbons. And then the enolate attacks benzyl bromide. And you get the benzylated derivative. Now, if there had also been H3O plus not workup, but legit reaction with H3O plus, this were reacted with H3O plus, so if this had said 3H3O plus, if there were a third step here that said H3O plus, then the acid will hydrolyze both esters, decarboxylate, and tautomerize the resulting enol to the keto form. And you will get the hydrolyzed and decarboxylated species. This then would be a malonic ester synthesis, which we did in class just today in Monday, Wednesday, Friday. So you need to look and see whether you're given H3O plus as a reagent. If you are, then it will hydrolyze both esters, decarboxylate, and tautomerize, and give you the acetic acid derivative in the case of malonic ester synthesis, or the acetone derivative in the case of an acetoacetic ester synthesis. But this did not mention H3O plus. It did, it said workup. That means not a full reaction. That means we just add enough H3O plus real carefully just to neutralize everything. We're not hitting it hard enough. We're not heating it. We're not hitting it hard enough to hydrolyze the esters. So without H3O plus, you just alkylate. With H3O plus, you do all the other stuff. So far, so good. Questions on any of those three? So let's do the other one. This next one is acid hydrolysis of a nitrile. And the compound that you get is a carboxylic acid. So that's that one. This next one, we have an alcohol and an acid chloride. That's what you need to notice. So this next one is alcoholysis of an acid chloride. I even remember where you can find that, 21.4. And so the product's going to be an ester. And so this carbon here is this carbon here. The alcohol reacts with the acid chloride to make an ester. And then last but not least, we have a nitrile and we have a Grignard reagent. Grignard reagents react with nitriles to make ketones. And the specific Grignard reagent that we're using is methyl Grignard. So this nitrile carbon becomes the ketone carbon. And this carbon is this carbon. You actually get an imine at first, but the H3O plus hydrolyzes the imine and gives you the ketone. That's a chapter 19 reaction. And that's basically it for that page. Make sense? Am I clarifying it enough? Again, I do not promise that you will get these same reactions. You have to expect the exam's not going to be the same as the practice exam. There should be some similar problems. Hopefully enough to make it worthwhile coming to the review session. Okay. Let's see. After this, I think we had the OWL style, or if you will, active style mechanisms. So I was real mean to them. I was a little tougher on them because the exam was open book. But I didn't really supply all of the molecules. I didn't supply the inorganic species, the ions. I only supplied the major organic species. So let's compare this first structure to this one and see what has happened. It looks to me like on this CH2, we've lost one of the protons. Now there's only one H over here. There had been two over here. There's now a double bond here and a minus charge on oxygen. Looks to me like we've pulled off this proton and made the enolate. Remember, no H on the oxygen and a minus charge, so it's an enolate. So this is going to complain. There's our CH3O minus that comes from the sodium methoxide. Sorry to always harp on it, but again, you'll notice I'm not even acknowledging the sodium. I didn't write it down anywhere. It's a non-factor. So the methoxide pulls off this proton. The electrons fold in to form a pi bond. We break the carbon-oxygen pi bond and put the electrons on oxygen. And that gives us this species. Now let's again compare and see what's happened. Looks like we formed a new bond here, alpha to the carbonyl, and we've reformed the carbon-oxygen pi bond. And instead of C double bond O, we have C single bond O minus. Looks to me like the enolate has added into the carbonyl. In chapter 23, we'll learn this is an aldol reaction. But you don't need to know that to get this question right. This folds down here. This attacks the carbonyl. And the carbon-oxygen pi bond breaks and the electrons go into oxygen, and we get this intermediate. And then if we compare, it looks like we formed a new oxygen-carbon bond. It looks like the oxygen has attacked this carbon and undergone an SN2 reaction. Losing the chloride ion, and we get the epoxide. And that all makes sense. The problem says one of the mechanisms involves an enolate. There's your enolate. The other one involves a resonance-stabilized carbene. Carbenes are bizarre species. They show up in chapter 10, and I don't know whether your professor went over carbenes. But carbenes can sometimes be made by an alpha elimination, which is very rare. Not cooperating. Okay, finally. So the methoxide pulls that proton off. This time the electrons go onto carbon, and we lose the chloride ion. So that carbon both gains and loses an electron pair. And you get a bizarre species known as a carbene. There's only 6 electrons around carbon. It's a neutral electron deficient carbon. Bizarre and pretty rare. And I would never have asked this unless this were an OWL or active style mechanism. The way carbenes work, the carbon needs to both lose and gain an electron pair in order to be happy. So the carbene attacks the carbonyl carbon, and then the electrons in the carbon-oxygen pi bond break and stay attached to the oxygen and form a bond to carbon. So the formation of that 3-membered ring happens in one step. Bizarre, strange, but true. And I could check the answer key, but I'm pretty confident I'm right. And that's the practice exam. We still have 20 minutes. So I can go over mechanisms. Students are telling me they lose the most points on mechanisms, so I want to drill mechanisms as much as I possibly can. Everyone okay with these mechanisms, though? Let's close this out. I think we can close ChemDraw. No, I don't want to save changes. We'll close the answer key. We'll close the exam. No, I don't want that picture to be available. Let's see. So this first one is Fischer esterification. I'm in the chapter 21 class notes. I want to go over as many mechanisms as I can, so I think I'll just basically reteach it from the class notes where the mechanisms are already drawn. So we're reacting our carboxylic acid. It doesn't have to be benzoic acid. It could be any carboxylic acid. And we're reacting it with an alcohol solvent with an acid catalyst that makes some of the conjugate acid of the alcohol. And so the first step, as is so often the case in acidic solution, protonate the carbonyl oxygen. And you use whatever the acid is that you're given. This is EtOH2+ over here. That's the species that you're given. That gives us this intermediate. After protonating the carbonyl oxygen, then you generally get nucleophilic attack. So you have to look back at what you're given and figure out what your nucleophile is. The only nucleophilic species is the ethanol. Don't make the mistake of using ethoxide. There's not going to be any ethoxide in acidic medium. It's too strongly basic. So we use an ethanol molecule as our nucleophile. We attack the carbonyl carbon, break the pi bond, and get this intermediate. After the nucleophilic attack, we generally have some proton transfers. We need to get the proton off this oxygen and onto one of these two oxygens because we want to lose water as a leaving group. Every step in a mechanism has a reason, and that's how you remember which steps come next, by understanding the reasons behind them. It's too much to memorize. I've come to understand that, especially this year. It's too much. You can't memorize it all. You have to understand it. So we use ethanol as our base to pull off this proton and give us this intermediate. We've gone from a charge of +1 to a charge of 0, which is good. The next step is to protonate either of these two OH oxygens. It doesn't matter which, they're the same. And we use, again, the conjugate acid of the given alcohol in order to do that. That gives us this intermediate, and now this is ready to lose water. This is the whole point of the reaction, is to lose water in order to make an ester. And so the OH oxygen electrons push in, kick out water as a leaving group, and we get this intermediate. And then last but not least, we just show ethanol, which is our given solvent, pulling off the proton and the oxygen to give us the product. So that's Fischer esterification, and it says so in the class notes, Fischer esterification. And please do learn this mechanism as opposed to the book's mechanism. They are often unforgivably sloppy. Everyone okay with Fischer esterification then? There's a DCC reaction. I think we had alcoholysis of an acid chloride on the practice exam. So here it mentions alcoholysis of acid chlorides to form esters. So let's say we treated benzoyl chloride with acidic ethanol. And again, I could wish I'd used a different acid chloride. This is an alcoholysis reaction. And the reason for it is because acid chlorides are so reactive. So this is different from Fischer esterification. And we'll learn why acid chlorides are so reactive when we get into the middle of the mechanism. First step, protonation of the carbonyl oxygen again. We use the conjugate acid of the alcohol. Next step, our nucleophile attacks. Our nucleophile is the alcohol that we're given. Ethanol attacks that carbon, breaks the pi bond, and gives us this intermediate. Next, proton transfer. We need to get the proton off of this oxygen to get rid of that plus charge. That's the reason for the step, is to get rid of the plus charge. And so we use an ethanol molecule to pull that proton off and give us this intermediate. Now we can lose chloride. And this is why acid chlorides are so reactive, because when you get to the tetrahedral intermediate, you don't need to protonate the chloride. It's already a good leaving group. So the electrons from the oxygen on the OH fold in, and we lose chloride as a leaving group. Don't protonate it. We do not protonate halides. They are already good leaving groups. That gives us this intermediate. Last but not least, we pull off this proton using an ethanol molecule, and we have our ester. So I think this is overall fewer steps than Fischer esterification. There should be at least one fewer step. And over here, we have the very same thing going on, but with an amine. And so instead of an ester, we're going to get an amide. But it's the exact same reaction. First, we protonate the carbonyl oxygen. That gives us this intermediate. Then our nucleophile attacks. Our nucleophile is the amine that we're given. That attacks. And we get this intermediate. Then once again, proton transfer. We want to get the plus charge off of nitrogen. So we use an amine molecule to pull that proton off and give us this intermediate. Then, sure enough, loss of chloride again. That gives us this intermediate. The amine pulls off this proton in order to get rid of the plus charge in oxygen, and we get our amide. So this is aminolysis of an acid chloride. That's mentioned previously in the class notes. Aminolysis. And anhydrides react pretty much the same way as acid chlorides. They're almost, but not quite as reactive as acid chlorides. Next big mechanism is acid hydrolysis of esters. So there's your hydrolysis. And it mentions acidic solution over here. Oops. So all we're given is the ester and H3O+. That means the three species we can use are the ester, H3O+, and H2O. Those are the only three species we can use in our mechanism. So we start by protonating the carbonyl oxygen, just as is generally the case in acidic solution. And with H3O plus, we know we're in acidic solution. So we protonate the carbonyl oxygen using an H3O plus ion. That gives this intermediate. After protonating the carbonyl oxygen, then comes nucleophilic attack on the carbon. So the only nucleophile we have around is water. Water attacks the carbonyl carbon, and we get this intermediate. Next step, proton transfers. We need to get the proton off of this oxygen and onto the OET oxygen so that we can lose ethanol as the leaving group. That's the whole point of the reaction, is losing a molecule of ethanol. Since we started with an ethyl ester. If we had started with a methyl ester, we'd lose a molecule of methanol. But we need to do the proton transfers first. So first we use water to pull off this proton and give us this neutral intermediate. Then we use a hydronium ion to put a proton onto the ETO oxygen. That way we'll be able to lose ethanol as a leaving group. And that gives us this intermediate. And that's when we lose ethanol. Ethanol leaves, the lone pair from the OH oxygen folds in. It doesn't matter which OH you do that with, they're the same. And you get this intermediate. Last but not least, we use a water molecule to pull this proton off to get a neutral compound, and we have our carboxylic acid. So that's how ester hydrolysis looks in acidic medium. It really is Fischer esterification run exactly backwards. Step for step backwards. They're the same reaction, they're just the reverse of each other. And you can tell which you're going to get by looking at what you're given. Over here, we're given an ester and essentially water. That means we're going to hydrolyze the ester. Since we're starting with an ester, we're going to hydrolyze it. Back here, we were given a carboxylic acid and an alcohol. And we need to know that carboxylic acids react with alcohols to make esters. So a carboxylic acid will react with an alcohol in the presence of an acid catalyst to make an ester. Here we're given an ester. And so it reacts with water in the presence of an acid catalyst to give us a carboxylic acid and an alcohol. In alkaline solution, the reaction looks a little different. I've changed the molecules around. Now, instead of ethyl benzoate, we've got methyl hexanoate. So this is alkaline hydrolysis of an ester, also called saponification. And alkaline conditions mean that we should not invoke any cations. So we do not protonate the carbonyl oxygen first in basic solution. We just do our nucleophilic attack. Hydroxide attacks the carbonyl carbon, and we get this intermediate. And then, in the next step, we can lose methoxide as a leaving group. You could never do that in acidic solution. You can't have methoxide in acidic solution. It's too strongly alkaline. But in alkaline solution, we're A-OK to lose methoxide as a leaving group. Methanol is a pKa of around 18, 19. We're at pH 14. We're within those 7 pKa units. So we're OK losing methoxide as a leaving group. The methoxide will very quickly pick up a proton from water to make methanol. The other species that we get from this is a carboxylic acid. And since we're still in alkaline solution, this is yet another one of those cases where we've generated an acidic species in alkaline solution. And so the base will deprotonate the acid, and we need to show that. So hydroxide pulls the proton off of the acid, and we get the carboxylate ion. And that carboxylate ion will swim around quite happily in our solution until we add acid. The acid will first neutralize the hydroxide and then start putting protons on the carboxylate. So the carboxylate pulls a proton off of H3O+, and we get the carboxylic acid. And I don't think I can do this whole mechanism in 3 minutes. So I'll do it, and if it goes over by a few minutes, it goes over by a few minutes. I taught you nitrile hydrolysis because in so doing, you automatically learn amide hydrolysis. So this is how nitrile hydrolysis looks in acidic medium. There is no oxygen to protonate, but there is a nitrogen. So we'll protonate that first. And that gives us this. Then water attacks the nitrile carbon just like it would attack a carbonyl carbon. That gives us this intermediate. Next, proton transfers. First, we use a water molecule. Remember, H3O+ implies that H2O is present. So we use H2O to pull off this proton and give us this intermediate. Then we need to get another proton onto the nitrogen because we need to lose the nitrogen as a molecule of ammonia. So this arrow means that the electrons on the oxygen are coming in to form a carbon-oxygen double bond. And we break the carbon-nitrogen double bond and use those electrons remaining attached to nitrogen in order to pull a proton off of H3O+. And that gives us this, which lo and behold is a protonated amide. If that H were not there, it would be an amide. And if you added an amide to H3O+, the first step is putting this proton on. So this way, by learning nitrile hydrolysis, you learn amide hydrolysis for free at the same time. So since now our oxygen is already protonated, we now have attack by a second molecule of water to give us this intermediate. Next, proton transfers. We first pull the proton off of the oxygen because we don't want the oxygens protonated. Rather, we need the nitrogen protonated. So we use an H3O+ ion to put a proton onto the nitrogen. That gives us this intermediate. And then we can lose ammonia as a leaving group. So this electron pair and oxygen folds in. We break the carbon-nitrogen bond and lose ammonia as a leaving group. That gives us this intermediate. And then all we need to do to get the carboxylic acid is to pull that proton off. And the electrons go back onto oxygen, getting rid of the plus charge. And I also gave you the mechanism in base. The idea is very much the same, except we're going to allow for anions since we're in basic solution. But the steps are very analogous. In the middle of the mechanism, lo and behold, we have an amide. So in hydrolyzing a nitrile, you get an amide halfway through. So the rest of the mechanism shows you hydrolysis of an amide in basic solution. Actually, I think there was one like this on the practice exam, because I remember talking about this intermediate. And that's basically it for chapter 21. I'm afraid we don't have time to go over all the chapter 22 reactions, but I figured chapter 21 would be better since it was further back. Chapter 22 is fresher in everyone's memory. So Any other questions? I'm sure you all have other things you'd rather be doing on a Friday night. So I hope that worked out well for everyone. And I guess I will see you all in class.